Hello and welcome to this revision session for AQA A-Level Physics Paper 3 on practical skills. So in today's revision session we're going to look at how to answer examination style questions for A-Level Physics Paper 3 on the practical skills aspects. So if you've been successful and you've learned in today's revision session, you should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and understand what topics you need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on this right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for your A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. You might wish to make mind maps or to write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge. You may wish to do this from your own cue cards. And then the third step is to use examination questions to look and test your knowledge. So use exam prep books, homework books, supervised study books, additional workbooks to see if you can answer examination questions and then mark your own work. And you might wish to download your own examination past papers to do this. Now, the three steps of learning the key facts, so using your revision guides, mind maps, write down notes yourself, testing yourself, and then writing and then practicing exam style questions are how you should revise for your A-Level Physics. Now, the questions we're going to cover in this revision session have three different stages. The first stage is the general check stage, which are the basic questions designed to probe your understanding of the key concepts of the topic. The second step is the checkpoints questions, which are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And the third step is the assessment point questions. These are past paper examination questions which will mimic the type of questions found in public examinations. So let's have a look at some practical skills questions. So the first question says, electrical experiments usually involve the readings of meters such as voltmeters as shown. What is the reading shown by each voltmeter and the uncertainty in each reading? Now, the voltmeter shows the readings obtained when they're connected across two wires which were identical apart from the different lengths. The current in each wire was 0.500 amps and the length L of the wire was 30.0 centimeters in the right diagram and 50.0 centimeters in the left diagram. Use the scale readings to test the hypothesis that the resistance R of the wire is proportional to the length L. Consider the effect of uncertainties on your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to be able to read analog meters. So it is 1.1 plus or minus 0.1 volt and 0.7 volts plus or minus 0.1 volt. Remember, because it's a reading, the absolute uncertainty is going to be, as you look on here, okay, it's going to be one of those divisions. So it'll be 0.1 there because that's the division shown here because you're looking at it twice in that voltmeter. Now, if we know K, if we know R equals KL, then the two values of K are going to be the voltage divided. We can work it through. So you could look at the resistance. So you would do R equals V over I. So you've got the values of V from the previous question. You've got I because you're told the current. So you can work out the values of R for both values, and then you divide by the length which was given to you as 30 centimeters and 50 centimeters. So you get your two values of K. Now the criterion is that if the resistance is proportional to length, then the percentage difference in the values of K will be less than the percentage uncertainty of the values of V. So if you look at the percentage difference in K, it's 0.27 over 0.044, so therefore it's 0.6%. So the percentage uncertainty, the lowest value of V is 14%, so it indicates to us that the data would be consistent with R being proportional to L. Now the next question says, an electronic engineering technician has been asked to determine the signal to noise ratio value of a signal generator. 4 signal generators have been tested and the results of the test can be represented by 2 log 3 plus log 4 equals log A plus 4 log 2. Solve the equation to find the value of A. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can use the rules of log in your Physics Practical 3 paper. So you would say, you write out the equation and you know x log y equals log y to the power of x. So straight away we've got log 3 squared plus log 4 equals log a plus log 2 to the power of 4. So that's going to be log 9 plus log 4 equals log a plus log 16. We know when you have log x minus log y, it becomes log x over y. And log x plus log y equals log x times y. So therefore we can see it's going to be log 36 equals log a plus log 16. So therefore log a equals log 36 minus log 16, which is log 36 over 16. So therefore log a equals log 2.25. So therefore a will equal 2.25. The next question says the amount of data received in the digital signal is given by the following formula. I equals log 2 over p minus log p to the power of power of 3, where I is the amount of data in the signal and p is the chance of receiving the data. Calculate the value of I when p equals 0.5. So pause the video now, then unpause the video when you want to go through your answer. Once again, you've got to be able to use the laws of logarithms in your answer here, which is needed for physics paper 3. So I is going to equal log 2 over p minus log p cubed. So therefore we can say that we can separate out log 2 over p as log 2 minus log p, and we can say log p to the power 3 is 3 log p. So therefore we can say I equals log 2 minus log a half minus 3 log 0.5. So you pop in all the values, work it through, and I is equal to 1.5. The next question says, the rate of discharge of a capacitor can be represented by the following expression. E to the power 2x equals 6. So solve the equation to find the value of x. So pause the video now, then unpause the video when you want to go through your answer. So in this one again, you've got to be able to use natural logarithms and exponentials in physics paper 3 to help answer questions. So if we say e to the power 2x equals 6, well, you take the natural log of both sides. So therefore the natural log of e just makes the power term become a normal term in the equation. So 2x equals log 6, x equals log 6 over 2. So therefore x is going to be equal to 0.90. The next question says, a student has taken measurements from a piece of wire. She measured the diameter d using a micrometer. She obtains the following readings. Explain how you'd use her readings to obtain the most accurate mean value for the diameter of the wire. Use her readings to obtain the most accurate mean value for the diameter of the wire, and then estimate the percentage uncertainty in your value for the diameter of the wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand what you would do to get an accurate mean value. So you ignore any anomalous data, you then add the non-anomalous data and divide by the number you add up, which was in this case 4. So when you work it through, you work those values out, you discard the anomalous one, so you get 0.27 millimeters. The number of decimal places is the same as the readings that are given, and so your percentage uncertainty is going to be 0.02 over 0.27 times by 100, which is 7%. Why is the absolute uncertainty 0.02? Because in repeats, the absolute uncertainty is the range divided by 2. So when you work that through, you're going to get 0.02. The next question says, the apparatus shown in the figure can be used to test the hypothesis that t, the time taken for the ball to roll down a plane from rest, is related to the distance s by the formula t squared equals ks, where k is a constant. The ball is timed using a stopwatch over 2 different values of s. Suggest problems with the experiment and how they may be overcome. You should consider problems in measuring the distance as well as the time. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware of how you could consider what experimental errors you would get. So apart from taking only 2 readings, which isn't enough, you need at least 5, it's difficult to release the ball without pushing it, so giving it initial velocity. It's difficult to start the stopwatch exactly as the ball is released. You might stop the stopwatch exactly as the ball crosses the line, but it's unlikely that's going to be the case. You might not release the ball exactly on the line. The times are going to be very similar to reaction times, so that's going to be a big percentage uncertainty. The ball might roll down the side of the track. You might have a parallax error when measuring distances. So improvements could be take 5 readings of s and plot the graph of t squared against s, because that'll allow you to see the value of k. You take a video of the ball rolling down the ramp with the timer and play it back frame by frame. You could use a metal ball held to an electromagnet at the same start position each time, and then turn off the magnet to start the ball. You could use longer distances to reduce the percentage uncertainty. You can have a groove down the middle of the track, and you could always view directly from above a mark on a track when using a rule to reduce the effect of parallax error. The next question says, the resistance R of a light-dependent LDR, light-dependent resistor, varies with the distance d from a very bright source of light. It suggested that R and d are related by the formula R equals kd to the power of n, where k and n are constants. Design a lab experiment to test this relationship. The LDR has a resistance of 50 ohms in bright light and 200 kilo ohms in the dark. So pause the video now, then unpause the video when you want to go through your answer. Right, when you're looking at this, always consider the following with when you're writing up a method: what the variables are, what the measurements will be, an analysis of what you do with the data, any safety procedures, and anything extra you might want to say. So in this investigation, the variables are, the dependent is R, the independent is D, and the control variable will be the light intensity of the bulb. For the measurements, you draw a circuit diagram and indicate that current and potential difference will be measured. The distance D between the source and the LDR will then be changed. D will be measured and shown, and then you think of a method of measuring D, probably with a meter ruler. Now, because you need to work out a value and you've got a power term in there, it's probably good to use logs. So you can either use natural log or you could use log base 10. So you draw a graph of log R against log D, and it should be a straight line, and you can work out that the gradient is going to actually be the power. The safety precautions would be avoid touching a hot lamp, or don't stare at the bright light. And extra things, just think about what currents you would be having, and then a choice of sensible meter ranges for your ammeter. Remember that the lamp is a line filament, and you've got to think about heating up over time. Think about how you'd measure the distance of the filament inside the bulb, not just the actual bulb itself. You do repeat measurements taken average. You do trial experiments to find a sensible distance to use the light against, and you're going to have to think about the issues of outside light affecting the experiment as well. The next question says, a ruler with a small mass at one end is clamped at the other end as shown below, and it oscillates up and down when plucked by hand. It suggested that the relationship of oscillation T of the ruler is related to the length by the relationship T equals KL to the power of n, where K and n are constants. Design a lab experiment to test this relationship and to find the value of n. So pause the video now, then unpause the video when you want to go through your answer. Right, like the previous experiment, what do we know? Well, the variables will be, the dependent variable will be the time, the independent variable will be the length, and the control variable will be the mass. So what would you do? You displace the mass downwards and release. You think of a method of measuring the length using a ruler, and a method to measure to the centre of mass of the actual object. You wouldn't just do one oscillation, rather you do multiple oscillations and divide by that number, and you'd use a stopwatch to do that. Because you want to find n, which is a power in the particular equation, you would do a graph of log t against log n, and the gradient of the line will be that power, it'll be n. Our safety precautions are probably going to be the masses falling off and hitting your foot, or the ruler breaking if there's a large amplitude of oscillation. So therefore, what extras could you mention? Well, use small amplitudes. Try the experiment to find sensible values of mass. Use an electronic timer, because again we're using an oscillator. We'd think about a fiducial marker, and also you'd measure the time from the center of the oscillation, as that's when the oscillator is moving the smoothest. The next question says, a current carrying coil produces a magnetic field. It is suggested that the magnetic field strength B at the center of the coil is proportional to the current I in the coil. Design a lab experiment that uses a Hall probe to test this relationship. So pause the video now, then unpause the video when you want to go through your answer. And once again, let's break down our method into the following stages. The variables, the dependent variable will be B and the independent variable will be I. Our control variables will be the coils, turns, and the area. So for our measurements, we have a diagram indicating coils and Hall probes connected to a voltmeter. The coil will be connected to a DC power supply, and you'd have an ammeter in the circuit to measure the current. You'd have your probes at right angles to the direction of the field to get the maximum change in flux linkage, and then think of a method to locate the centre of the coil quite accurately. You then draw a graph of B against I, or log B against log I, and really you should get either a straight line through the origin if it's B against I, or log B against log I should have a slope of a gradient 1. So the safety precautions would be a large current would cause heating, and so you'd switch it off when not in use. You'd have to think about a method to create a large magnetic field, so probably have a large current going through it. You'd have to think of a method to keep the probe in the same orientation, so use something like a set square to make sure it's orientated correctly. You'd have your Hall probe calibrated correctly. You'd repeat the experiment with the probe reversed, and you'd also try to avoid any external magnetic fields. The next question says, complete the following task to assess your understanding on data analysis. The time t taken for a trolley to travel distance s is measured 5 times. Table 1 shows the results. Calculate the mean time and the uncertainty in these measurements. The trolley and mass are released from rest and travel a distance measured to be 0.750 meters. The uncertainty in the measured distance is plus or minus 0.002 meters. The acceleration is given by a equals 2s over t squared. So calculate a and its percentage uncertainty. So pause the video now, then unpause the video when you want to go through your answer. So, how would you answer this first question? Well, to calculate the mean, you would add up all the values and divide by the number of values you add up by, so you get 0.79. Remember, 2 decimal places because the values are given to 2 dp. The uncertainty is the range divided by 2, so you look at your values, you do your range, which is going to be 0.04, you divide it by 2, so it's plus or minus 0.02. Now, this next question is a bit harder, so you firstly work out what a is by doing 2s over t squared. You've just worked out what t is, you're given s, so it's 2.40 meters per second squared. Now, the percentage uncertainty in a is going to be the percentage uncertainty in s plus the percentage uncertainty in t squared, because they're dividing it, but because it's t squared, it's the percentage uncertainty in t times by 2, because that is what the power is. So you work that through and you get plus or minus 5.3%. Now the next question says, a ruler graduated in millimeters is used to determine x. The student places the ruler on the floor with the zero graduation aligned with p. The student determines x when the ball is released 6 times a particular value of h. He makes marks on the floor where the ball lands. Figure 5 shows the circle that indicate these marks. Determine x for this value of h. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question they are going to ask you to make measurements in your experimental data on the exam. So what you've got to note is, firstly, there's an anomalous data set there right on the right hand side that is not precise compared to the other repeats, so you will discard it. So the first thing you do is reject the anomalous mark at 607. You will then calculate the mean from the other readings, make sure to read up the scale and not have a parallax error, and you work out the answer to be 584 millimeters. The next question says, figure 1 shows the micrometer screw gauge. What is the reading on this micrometer? And then a metal wire of diameter d is held in the gap between the anvil and the spindle. Just before a reading of d is taken, the gap is closed using the ratchet and not the thimble. Explain why the gap is closed in this way. So pause the video now, then unpause the video when you want to go through your answer. Right, so you can see that on the main scale each value is 0.5 of a millimeter, so it's past 5, so it's 5.5, 6, 6.5. You then add the point value of what is shown on the intersection between the micrometer scale and the main scale, which is 0.25, so you add the two together to get 6.75. Now, you've got to think of the good technique to use a micrometer screw gauge. So cause the wire to be distorted or damaged, reduce the diameter, and give an improper reading. Now the next question says, a ball is released from rest and then continues to roll at a constant velocity across a horizontal table as shown. The bottom of the track is fixed to the table at point Q. The angle between the straight part of the track and the table is alpha. A marker is placed at R, a point midway between Q and the edge of the table. The student uses a stopwatch to measure the time t for the ball to roll from Q to R. Explain why increasing the distance QR will reduce the percentage uncertainty in t. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a key idea that you can reduce percentage uncertainty by having a larger value. So the absolute uncertainty in the measurement is the same, but the value of t is larger, decreasing the percentage uncertainty. Now with this information you can see that at a particular value of alpha the ball rolls from Q to R at its maximum velocity. Explain how the student should use this figure to determine the value of alpha. Go on to suggest what further readings should be taken to reduce the uncertainty in this value of alpha. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware that the value of you can have the maximum velocity when the value of t is the lowest, because the fastest time it does it in will give it its maximum velocity. So you draw a line of best fit or curve of best fit and read off alpha where the value of t is a minimum, because the lowest time will give you the highest the highest velocity, the maximum velocity. Now as well, remember, because you are wanting to look for the lowest value, the minimum value, you would take more readings around alpha where t is a minimum. There's no point just taking values in general, it's around that particular point, so that's how you get a more accurate value. Now the next question says, a student made measurements of a circular convex lens as shown. The student used vernier calipers to measure the diameter d. Explain one technique you should use to measure d. Then the student estimated that the thickness t of the centre of the lens was approximately 5 mm. Explain the most appropriate instrument the student should use for a single measurement of t. Your answer should include a calculation. So pause the video now, then unpause the video when you want to go through your answer. So, how do you answer this question? Well, you've got to think about how you would use the vernier calipers correctly. Now, when you're trying to measure a value such as diameter, you've got to think to repeat it at different orientations and at different parts of the actual shape. You will then calculate a mean to reduce the effect of random errors, and you also should check and correct any zero error on the calipers to eliminate any systematic error. Now, to show it's an appropriate instrument, you've got to do a sample percentage uncertainty calculation. So you do your percentage uncertainty, which is the absolute uncertainty divided by the value, times by 100, which is 0.1%. So therefore, because that percentage uncertainty is small, we can conclude that the value itself is that the instrument is suitable to use. The next question says, figure 9 shows a spoon used to measure the mass of food. The empty spoon balances when a pivot is placed under a point P halfway along the spoon. The spoon tilts when the food of mass M is placed in the bowl. The spoon is rebalanced by moving a pivot along a distance x to the right of P. The new position of the pivot is under point Q in the figure 10. The total length of the spoon is 32.0 centimeters. The weight of the food acts at a line at the distance of 4.0 centimeters from the right hand edge of the spoon. Figure 11 shows how x varies with m. A scale in grams is marked on the spoon between P and the bowl. Figure 11 is used to calibrate the scale in intervals of 25 grams. M can be measured by balancing the spoon. The value is read from the point of the scale directly above the pivot. State and explain how the uncertainty in the value read from the scale changes as m increases. So pause the video now, then unpause the video when you want to go through your answer. Right, you can see that the absolute uncertainty in m increases as m increases because m is getting bigger. So because our absolute uncertainty is increasing, the marks on the scale are getting closer, or you would say that the range of values for m for a fixed range of x will increase. So therefore the gradient will increase. So therefore what it's telling us is because the gradient is curving upwards, well then the scale markings shown on the device will actually not be equal, they'll be unequal, with them getting closer as the value of m increases. The next question says, figure 3 shows a circuit used to find the resistance per unit length of a copper wire. The copper wire is fixed with tape to a meter ruler that has 2 mm graduations. Contact P is placed on the wire close to the one end of the ruler and held firmly in place using a bulldog clip. When contact Q is placed on the wire as shown, the voltmeter shows a non-zero reading. Q is then moved along the wire until the voltmeter reading is 0. Figure 4 shows enlarged views of the position P and the new position Q. Determine in meters the length x of the copper wire between P and Q. So pause the video now and unpause the video when you want to go through your answer. Right, you should see that the starting value is going to be from the far right hand side of P from the diagram given. So you can see the starting value when you read off the scale is 6.7 centimeters. The final value is the furthest left of the contact Q because it's between the 2 points. So therefore it's 94.2 when you read off the scale, and therefore the length of the device is the difference between the two. So you get 87.5 centimeters, but once it in meters, it's 0.875 meters. The next question says, well, the diameter d of the copper wire is approximately 0.4 millimeters. Suggest a suitable measuring instrument to accurately determine d, and then how to reduce the effect of random error on the result for d. So pause the video now, then unpause the video when you want to go through your answer. Right, well, you're going to measure something which is on the scale of 0.1 millimeters approximately. So you want to pick either a micrometer screw gauge or a vernier caliper to do this. Now, like we said before, you'd repeat it at different points along the wire in different directions and different orientations. You then repeat the measurements, reject anomalies, and then calculate an average or mean from the measurements. That's how you get an accurate value. The averaging will reduce the effect of random errors. The next question says, complete the following task to assess your understanding on this area of A-level physics. The table below shows the measurements recorded by the student to determine the percentage uncertainty in these sets of data, and then the student's results are shown below. Determine the percentage uncertainty in the result the student obtains for W. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how to work out percentage uncertainty? Well, the first thing you do is you find your mean time for 20 oscillations. So you work it through, you add up all the values, you divide it by 5, you get 22.7. Now the uncertainty is half of the range, so you get that to be 0.3. So therefore your percentage uncertainty is 0.3 over the average 22.7 times by 100, and we get 1.3%. In our next set of data, what we can look on here is if we look back onto here, sorry, go the wrong way there, you get 1.2%. Why is that? You'd work out your average value by adding them all up and dividing by the value. You then do half the range, multiply it by 100, and you get 1.2%. The next question says Ellen drops a ball from a height of 1.20 meters and 0.80 meters and measures the rebound height using a meter ruler of resolution plus or minus 0.01 meters. She obtains the following results. Ellen predicted that the rebound height would be directly proportional to the drop height. Without drawing a graph, explain whether Ellen's results supported her prediction and describe one way in which Ellen could improve the experiment to obtain more accurate results. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you can find if something is directly proportional by dividing the two values by each other and see if it's a constant value. So you do the rebound height over the drop height, you find the two ratios, you get it completely different, give your conclusion it's not the same constant, so therefore it's not proportional. How could you make it more accurate? You could use freeze frame photography, slow motion cameras, a release mechanism, a use of an assistant to help you, or drop it from a greater height if possible. The next question says a student used a transparent tube to measure a volume of liquid as shown. Open the tap allows the liquid to flow out the tube at a controlled rate. When the tap is open, the volume V of the liquid inside the tube decreases with time according to the relationship V equals V0 e to the power minus BT, where V0 is the initial volume of the liquid in the tube and B is a constant. Explain why a graph of log V against T should be used to test this relationship. A student investigated the relationship between V and T. Describe how the student could obtain an accurate set of values for V and T to test this relationship and explain a source of uncertainty in the investigation. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, what will we say? Well, because we've got natural log V against T, well, we can say that, right, well, let's take natural logs of both sides of the equation. So we get log V equals log V0 minus BT. That's because we can separate out V0 e to the power minus BT, because when they work through, there'll be times, so you'd add them, but because there's a minus BC, it become a minus. Now, natural log E cancels through, and just the power becomes a normal term. So log V equals log V0 minus BT. You can put that in the equation y equals mx plus c. So therefore our gradient is going to be minus b and our y-intercept is log v0. Now how do you do the experiment? Well, you'd open the tap, start recording the time simultaneously, record the volume at successive time intervals, always think accuracy, so read to the bottom of the meniscus, ensure the transparent tube is vertical, so think about that accuracy as well, use a stopwatch to measure t, keep the stopwatch close to the tube and refill to the same initial volume and repeat each time to take a mean and record many measurements of v and t, open the tap to the same position each time. Now what issues are, it can be difficult to measure V and T simultaneously, which would affect your random error. There will be liquid below the scale, which induces systematic error, and air could be trapped in the tap, which would be a random error. The next question says the relationship between P and V for a filament lamp can be expressed by the equation P equals KV to the power of N, where N and K are unknown constants. Your task is to write an experiment to determine N and K. Write a plan of how you obtain sufficient readings to determine N and K. You will need to include a circuit diagram, risk assessment, and how your results would determine N and K. So pause the video now, then unpause the video when you want to go through your answer. Right, for this experiment, you're going to think about how you could get different values. So you'd adjust your rheostat and you record V against I. So if you look at your circuit diagram, you'll have an ammeter, voltmeter, bulb and a rheostat in the circuit with the power supply. You can work out the power by doing P equals VI. Now, because we know that from the equation, you can see that P equals KV to the power of N. So therefore, if we do a log of P against log V, well, therefore the gradient of the line will be the power. So therefore it'll be N, and the Y-intercept will be the log of the value times by that term, so it'll be log K. Now in terms of risk assessment, the hot lamp can burn, so touching the lamp can burn the skin, so you'd leave the lamp to cool before you would move it. The next question says, you're going to investigate how the time taken for a marble to roll down a slope depends on the distance travelled x and hence finds acceleration a. The height of the track above the bent h has been set for you and should not be adjusted. If the marble starts from rest, it can be shown from theory that x equals at squared over 2, where t is the time taken for the marble to roll a distance x and a is its acceleration. Write a plan of how you carry out investigation to do this. Include a risk assessment with your plan. So pause the video now, then unpause the video when you want to go through your answer. Right, again, so you would take a trial reading and then record between at least 1 metre and 0.60 metres. Repeat reading should be taken, have a suitable range, so it's got to be between 1 metre and 0.60 metres. Release the marble, stop the stopwatch when it hits the clamped area and record the time. Now, because we want to find out the relationship, you plot x against t squared, the two variables. If the relationship is true, well, a and 2 are a constant, so therefore you get a straight line through the origin. Now, a risk would be that the marble is dropped so it could hit the experimenter, so you would stand back as the marble falls. The next question says, a spring has a spring constant K equals 240 newtons per metre, with a tolerance of plus or minus 5% supplied by the manufacturer. The maximum energy that the spring can store safely is 90 joules. A lab technician uses the spring in an experimental arrangement and measures the extension with a ruler that has a resolution of plus or minus 1 centimetre. The extension is recorded as 85 centimetres. Determine the energy stored in the spring along with its absolute uncertainty. Explain why this might not be safe. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you got to think about is how do you work out the energy stored in a spring? Well, work done is, in this case, it's a half kx squared. So you'd work it through and you get 86.7 joules. Now, your percentage uncertainty in the work done is going to be the percentage uncertainty in k plus 2 times by the percentage uncertainty in x, because it's x squared. So you work it through. Now, you're given the tolerance of k to be plus or minus 5%. You know what the uncertainty in the extension is going to be, because it's going to be 1 centimetre over 85. Times it by 2, because it's going to be the value squared, so multiply the uncertainty by 2, so you get 0.07%, so that's going to link it through to be 7%, so you find 7% of 86.7 joules, which is 6 joules, so if it's plus or minus that, it's 87 plus 6, or 87 minus 6, that's got to be above 90 joules, so you've got to say it will be unsafe. The next question says, a shallow tray holds water. The depth D of the water is about 2 centimetres. A student measures the distance across the tray as 33.4 centimetres with an uncertainty of 0.2 centimetres. She then determines T is 0.92 seconds with an uncertainty of 0.03 seconds. Use the measurements to calculate V, the velocity of the wave. Estimate the percentage uncertainty in your value for V, and the student is told that V squared equals KD, where K is a constant. She then measures the depth D is 2.1 centimetres and calculates a value for K. Use your previous answers to estimate a percentage uncertainty for K, and then it suggested that the value for K is equal to the strength of the gravitational field of the Earth, 9.81 newtons per kilogram. Use your calculations to discuss whether the result supports this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how do you work it through? So you say velocity is going to be distance over time. You've got those values, you get 0.363 meters per second. Now your percentage uncertainty is going to therefore be the percentage uncertainty in the distance, which is the absolute divided by the value, plus the uncertainty, the absolute uncertainty in the time divided by the value. Now we add them because when you divide values, you add your percentage uncertainty, so you add the two together, you get 3.9%. Now what's the value for K going to be? You rearrange it and you get K is V squared over D, so you pop the values in, you get 6.27 meters per second squared. Now the percentage uncertainty here again, you do your percentage uncertainty of the velocity times by 2 because it's V squared, so it's the answer you got previously, times by 2. You then add 5% because you then also, when you're looking through, dividing by D, so therefore you'd add the value, so it's 12.8%. Now in this last one, what's the percentage difference? Well, the percentage difference is going to be 9.81 minus 6.27, the difference in the two values, divided by the accepted value, which is 9.81, times by 136%. So we can see here the percentage difference between the two values is a lot greater than the percentage uncertainty in the measurements. So therefore we can say that the value for K is a lot outside the value of the tolerance for the value of G, so they can't be the same value. The next question says you're going to investigate how the static extension Z of a spring affects its period t. The static extension is the distance a spring extends without oscillating when a weight has been added. The relationship between the period of oscillation and the static extension Z can be expressed as t equals kz to the power of n, where k and n are unknown constants. By taking logs, rearrange the above equation into the form of y equals mx plus c and state which graph should be plotted to determine n and k. Then write out a plan of how you would carry out an investigation into the relationship t equals kz to the power of n, include a label diagram. So pause the video now, then unpause the video when you want to go through your answer. So, how do you answer this question? Well, firstly, you've got to think about, take natural logs of both sides. I mean, you could actually take a log base 10 of both sides as well, just as it does make a difference. So you would say natural log t equals n log z plus log k. Now, n can drop out to the outside of that to the multiplication because that's a rule of logs. So therefore, if you place log t on the y-axis and log z on the x-axis, well, therefore, you can work out what k is going to be, because log k is going to be the y-intercept, and the gradient of the line is going to be n. So what you do is, for this next question, draw a clearly labelled diagram with masses and the ruler and the spring drawn in there. You trial the readings with at least a minimum of one pair of results, and then you repeat the readings to be taken with a full range, so 100 grams to 500 grams, for example. You take a minimum of 5 oscillations for each weight and divide by the average to work it then through. The next question says a student places a circular convex lens in a holder. She sets up the apparatus as shown. The student moves the position of the holder until the lens formed a shape image of the wire mesh on the screen. She measured the distances u and v with a meter ruler. The student determined that the focal length of f of the lens using the formula uv over u plus v equals f. So show that the uncertainty in f is about 0.2 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing you need to do is work out the percentage uncertainty in U and in F. So you do your absolute uncertainty divided by the value taken times by 100. So you get 0.34% in U, 0.52% in V. Now, because you're going to have U plus V on the bottom line, you can work out what the absolute uncertainty of that total term is by adding the absolutes, because it's a plus, so you add the absolutes. So therefore you do that as your absolute, you then work out what the value is by adding the two normal values, then times it by 100, so you get 0.41%. So therefore F is going to have a percentage uncertainty of U, the percentage uncertainty in U, plus the percentage uncertainty in V, because they're being times together. You then plus the uncertainty in U plus V, because they're being divided, so and then still a plus in the percentage uncertainty, so you get 1.3%, and then you find 1.3% of the value of F, which when you work it through is 11.6 centimeters, so 1.3% is 0.15 centimeters. The next question says, a student investigated the inverse square law for the light using the apparatus as shown. The student used a meter ruler to measure the distance d between the filament of the bulb and the sensor on the light meter. The reading on the light meter is the intensity I of the light. Explain how two sources of error can be reduced in this investigation. The relationship between I and d is given by the equation I equals k over d squared, where k is a constant. Explain why a graph of I against 1 over d squared should be a straight line through the origin. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the two sources of error? Well, you can't measure to the centre of the filament lamp because there's going to be glass there, so you'd measure the diameter of the bulb separately and then add the radius to the measurement of d. You'll have a parallax error when measuring d with a meter ruler, so you should always use a set square and a sensor and the bulb, and making sure that your eyes are perpendicular to the meter ruler when you're taking measurements. The background light in the room will also affect the readings on the light meter, so you should be doing it in a darkened room or a covered room, so you can block off the background light, or you could actually measure the background light and subtract that intensity from the values. Now this will give a straight line through the origin, because we can see I equals k times by 1 over d squared, so we'll put that in the equation of y equals mx plus c. When you work it through like that, k is going to be the gradient of the line, and therefore there's no value for c, so therefore it's a constant straight line. There's nothing going, the origin is 0, so the y-intercept is 0, which is the origin, so therefore it's a straight line through the origin. The next question says, it suggested that the relationship between the electrical power P is transferred by the lamp and current is P is proportional to I cubed. Describe how you'd use your circuit to test this suggestion. Your answer should include the method you would follow, how you present your results, and an explanation of what you expect your results to show if the relationship is correct. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you do this? So firstly, you would measure potential difference in current for at least 6 values of PD between 0 and 6 volts. You record PD, you would record current. You then repeat it at least one time for the same values of V and then find an average value for current throughout. Then for each value of V, you can calculate your power with power equals IV. Now you could do a couple of things to work out whether the value is actually P is proportional to I cubed. You could plot P against I cubed, and therefore if they're directly proportional, it should be a straight line through the origin. Or what you could do is plot log P against log I, and then at that point we know that the gradient of the line produced should be equal to the actual term of the power, which is 3. So if you did that, you would get a gradient of 3. The next question says, a meter ruler with a mass attached to the free end is clamped to the edge of a bench as shown in figure 4. The ruler oscillates when the mass is displaced vertically through a small distance and released. Theory predicts that the period of oscillation t of a system varies with length L according to the equation t squared equals k to the L cubed, where k is a constant. Describe the procedure you would use to verify the equation. You may suggest the use of apparatus in figure 4 together with other lab standard equipment. Your answer should include details of the measurements to be made, the measuring instruments that you would use, how you would make your measurements accurate, and how you would analyse and interpret the results. So pause the video now, then unpause the video when you want to go through your answer. Right, so take each bullet point by itself. You take measurements of T for 6 or more values of L. You'd use the meter ruler to measure L. You then time 10 or more oscillations. You then repeat it and average it to get a measurement. That allows you to calculate a mean value of T. Now remember, you're working out you're doing 10 or more oscillations because it'll reduce the uncertainty because there's less random error. That allows you to plot a graph of t squared against L cubed, and then the formula will be verified if it was a straight line through the origin. The next question says, apparatus was used to investigate the flow of water through a narrow rubber tube. The lower end of the rubber tube was closed and a volume V of 120 centimeters cubed of water was poured into the funnel. The tube was opened and a stopwatch was used to measure the time taken for all the water to flow through the tube and into the beaker. This test was repeated 4 more times using V equals 120 centimeters cubed each time. The results are shown in table 1. None of the results are anomalous. So firstly, calculate T, the mean value for the time flow of water. Then calculate the absolute uncertainty in T. Then the average rate of flow of R through the tube was given by R equals V over T. Calculated meters cubed seconds to the minus 1, the value of R when V equals 120 centimeters cubed. Then the measuring cylinder was used to measure V with a resolution of plus or minus 2 centimeters cubed. Estimate the percentage uncertainty in your value for R. And then finally state what is meant by the precision for a set of measurements. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, how do you work out the mean value? Well, you add up all the values and you divide by that value. You look at the same root of significant figures, so therefore it's going to be 41.9. You could also add that second decimal place in there, 41.92, to be consistent with the measurements. Now, absolute uncertainty is going to be the range divided by 2, so you do your biggest minus your smallest divided by 2, and you get 1.4. Now to work out R, we're going to do V over T. Now you're going to have to convert centimeters cubed into meters cubed, so that's very important. So to go from centimeters cubed into meters cubed, you're going to times by 10 to the minus 2 cubed, because it's 3 times. So you do that, you divide it by the time. As you can see from the previous question, work out what the time is, 41.92, pop it all in, and we get 2.86 times 10 to the minus 6 meter cubed seconds to the minus 1. Now the next question is, how do you work out the percentage uncertainty in your measurement for volume? So what you've got to do here is find the percentage uncertainty in the volume, which is going to be about 1.7%. Now we can know that because we can see roughly what it's going to be. We can see that it's going to be 2 divided by 120 times by 100. Then R is V over T, so you find your percentage uncertainty in your time by doing 1.4 over 41.92 times by 100. Now because the two terms are divided in the equation, you would add the percentage uncertainties, so you get a value of approximately 5%. Now finally, what do we mean by precision? You've got to learn this. Precision is not accuracy. Precision is the variation in repeated measurements. So that brings an end to our revision session today. If you've been successful and you've learned in today's revision session, you should be able to answer A-level physics examination style questions on practical skills topics. You should be able to assess your understanding on A-level physics practical skills and understand what topics you need to improve upon for A-level physics in the practical skills. So that brings an end to our revision session today for AQA A-Level Physics Paper 3 on the topic of practical skills. Thank you so much and have a lovely day.